Assalamu alaikum dear students. I hope you're all fine by the grace of Almighty Allah. I welcome you all to the 28th lecture of Thermodynamics 2. Lecture 28. The contents of lecture 28 are gas power cycles, air standard cycles, engine terminologies, 2 and 4 strokes engine, ideal Otto cycle, numerical problems, and conceptual questions and answer. So in from this lecture we will be starting the second part of the chapter. So the first chapter part of the chapter comprises of power cycle that have the two-phase working substance. So in the first part we were discussing the vapor power cycle, and in this second part we will be discussing the gas power cycle. So the categorization and the classification of power cycle we have already discussed in the lecture number 25. So we have two types. So one is power generation and one is power consumption or refrigeration power cycles. Then we have the classification according to the working substance. So according to working substance we have a vapor power cycle. So in vapor power cycle we have generally we have the working substance as water. So in some part of the cycle the working substance is in the vapor or gaseous phase, whereas in some part the working substance is in liquid phase. So the second classification, according to the second classification, we have gas power cycles. So in gas power cycle we have working fluid as in the form of gaseous. So here it may be in the form of air or other gaseous substances. We will look into the details. And then we have the classification according to closed and open cycle. So the example given in the previous lecture was the vapor compression cycle. So it has four processes and it is a cyclic process. So it is a closed cycle process, whereas the example of automobile engine is the example of open power cycle, in which the working substance renewed at the end of each cycle, whereas in the closed cycle the working substance retained its state and move and gets back to its initial state. So from current lecture onward we will be discussing the gas power cycles. So gas power cycle, devices that produce work from heat source. So the according to the basic definition of thermodynamics, it's the science or part of thermodynamics consider the conversion of thermal energy into mechanical energy. So gas power cycle comprises of devices that produce work from the heat source. So there is certain amount of heat source. So it may be a high temperature reservoir and it may be a fuel combustion source. So we will drive mechanical work or produce work with the help of heat source. So in gas power cycle, as we have discussed previously, the working fluid in these devices remain in a gaseous phase. So some of the example given are spark ignition engine, diesel engine, and gas turbines. So we have two type of combustion engine. Some are internal combustion engine and some are external combustion engine. So internal combustion engine are those in which the process of combustion is happening within the uh, engine itself, An external combustion engine is the process in which the combustion is happening outside and the piston cylinder or mechanical work is happening in some other place. So basically both of these convert the thermal energy into displacement or mechanical work. So here the spark ignition engine is mentioned. So usually, as in the second example, it is written as diesel engine. So petrol engine is also known as spark ignition engine. So you may write here as usually spark ignition engine. So here we will write petrol engine are considered as the spark ignition engine, whereas in diesel engine are also known as compression ignition engine. So we will discuss in detail what are spark ignition, why they are known as spark ignition, why diesel engine is known as compression ignition engine. Then we will discuss a little about gas turbines, how they work, and when we will be discussing the external combustion engine, we will be discussing Stirling engine and Ericsson engine as well. So for gas power cycle, we will be performing an ideal cycle analysis. So similarly, when we were discussing Carnot engine, we were considering its ideal Carnot state, and in the previous half of the chapter of vapor compression, power cycle, vapor cycles. So we have initially discussed the ideal case and a Rankine cycle, ideal Rankine cycle, and then actual Rankine cycle. So similarly, we will adopt the same pattern. So initially, we will discuss about the ideal cycle analysis of gas power cycle. So the clauses or the points or main important highlights for this analysis is that no friction, mechanical or pressure drop or fluid friction is involved. So it is this assumption is somewhat similar to the assumption of Rankine cycle, in which we assume that there is no friction involved. So when we were talking about the fluid friction and mechanical friction, so in fluid friction there is no pressure drop, and in mechanical friction there is no friction present between the piston cylinder system, and it is a quasi equilibrium expansion and compression. So as you know that we have already studied what are quasi equilibrium, quasi static processes. So the expansion and compression process are happening at a very slow rate. So these I will write it here. So these processes are performed at very slow rate, very slow rate, because quasi equilibrium and quasi static processes are performed very slowly. So when we are compressing the working fluid or there is a process of expansion, so there is no molecule accumulation in the piston cylinder. So where the piston is moving, so there is no molecule accumulation. To avoid that, we will be using quasi equilibrium or very slow rate expansion and compression. Heat transfer is negligible when not indented. So there will be no heat transfer unless and until we want that heat transfer to happen. So piping and connecting component, they will be adiabatic. So I will write that the pipe and connecting components are performing as adiabatic. Heat transfer through a finite temperature difference, thus not externally reversible process. So as there will be a finite temperature difference, so here, so usually for to be externally reversible, the temperature difference between 2 points should be infinitesimally small. So we have already discussed about what are externally reversible and what are internal reversible and what are totally reversible process. So if the surrounding comes back to its initial state, then it is called as externally reversible, and if the system is come all the process happen and come into its initial state, then it is called internally reversible, and a process which is internal as well as external reversible is known as totally reversible. Air standard cycle assumption. The internal combustion engine, or usually internal combustion engine is also known as IC engine, operates on open cycle. However, for analyzing internal combustion engine, it is based to approximate the open cycle to a closed cycle. So in the start of the lecture, I have already told you what are open cycle and what are closed cycle. In a closed cycle, the working fluid retains its state and comes to the initial state, whereas in the open cycle, the working substance is renewed in after each cycle. But to simplify the process, we will assume the internal combustion engine operates on a closed cycle. So to approximate an open cycle to a closed cycle, there must be some assumption that we will have to follow. So these assumptions are known as air standard power cycles. So air standard power cycle assumptions, we will be following these. So the first assumption is working fluid is air. So we consider air as an ideal gas and circulate it in a closed loop. All cyclic processes are internally reversible. So I have already told you what are internal and external reversible and what is meant by total reversible. Combustion processes are replaced by heat addition from external source. So it is somewhat like to be in the Rankine cycle, we have a boiler in which heat is added from a reservoir source. So it's a constant supply of heat. So to approximate an open cycle to a closed cycle, here we will assume that the heat addition uh, is from an external source rather than the combustion process. Exhaust processes are replaced by heat rejection. So uh, after the combustion and the some of the thermal energy is converted into mechanical, whereas the rest of it is rejected into the sink or exhaust out. So the exhaust process for air standard cycle are replaced by the heat rejection process. So cold air standard assumption. So these are the additional assumption that may be used sometimes. So it may be mentioned in the numericals here, so that you have to assume the cold air standard. So what these assumptions say? So cold air standard assumption, this is very important. Sometimes it may be asked in the viva what is meant by cold air standard assumption. So we will discuss. So air have because it's compressible substance, so it's a value of certain values of Cp and Cv, specific heat and constant pressure and specific heat at constant volume. So as there is a significant variation of temperature throughout the cycle, so cold air standard assumption states that whenever we want to assume or use the value of Cp and Cv throughout the process, we take these value at the temperature of 25 degrees centigrade, and the value of Cp and Cv will remain constant throughout the process. Or otherwise it is mentioned, if we don't do that, the temperature difference is very high and we have to consult tables to verify the changing value of Cp and Cv. So here you must to give you a reference, so the value of operation or the value between the cycle process, the temperature change may vary between a couple of hundred to let's suppose the least temperature is 120 and the maximum temperature is 600. So there is a large variation between the temperature. So here the cold air standard assumption states that the value of Cp and Cv for air, we will take it as a constant. So usually the value of air Cp is 1.005. So we will see what are the values in the upcoming slide as well. So now we will discuss some of the engine terminologies that are vastly used. So this is a schematic diagram of piston cylinder system. So engine and piston cylinder system are somewhat similar, and there are many. In the upcoming slide we will show in animation as well. So here this part is known as piston. So the relative position of piston with the cylinder is termed as, so if the piston is in the uh, least position, so here it is the maximum position that it can come back, so this is position is known as bottom dead center, and the piston that can move maximum to the cylinder is known as top dead center. Here this is mentioned. So these are the some relative position of piston, whereas the diameter of the cylinder is known as bore. The motion of the piston from bottom dead center to the top dead center is known as stroke. So this is bottom dead center, the above is top dead center, and in between region is known as stroke. So there is some clearance area between piston and the cylinder boundary. So this is known as clearance area. So this is inlet manifold. So the working substance will be entering through the inlet manifold. These are valves, so we will discuss in detail what are the names of these valves. So the inlet manifold allows the working fluid to enter, and the piston will move to the bottom dead center. So in this entire area, as the piston is moved to the bottom dead center, this state, so the working fluid will fill all that area. Then the piston will move upward to the top dead center, and this will compress and increase the pressure and reduce the volume. So this motion will compress the working fluid. So the working fluid will only remain in this clearance area. Then there will be a process of combustion, and with the process of combustion, that working fluid will expand because there is a huge amount of energy that will be releasing corresponding to the combustion process. So that piston from top dead center position will move to the bottom dead center, and this is an exhaust outlet. As the piston will move backward, so this exhaust will open, and the bottom dead center piston will move upward again. So as it move upward, so all the exhaust gases will exhaust from these exhaust holes. So these are some engine terminologies. What is meant by inlet manifold? Inlet manifold is the inlet that allows the working fluid to enter into the piston cylinder. Clearance volume is the space between maximum height of the piston to the cylinder head. So this is the area between piston top dead center, when the position of piston is at the top dead center, and between the cylinder head. So this is the clearance volume. The maximum distance moved by the piston is known as stroke. The diameter of piston is known as bore, and the minimum position or the maximum position from cylinder head of the piston is known as bottom dead center. So all these terminology engine are known. So this is a animated diagram of this engine. So as you can see that there is a number going 1 2 3 and 4. So this means that it is a 4-stroke engine animation. So initially you will see when one, so blue gas is entering into the cylinder. This is entering, piston is moving down, then piston is moving up. For compression there will be a spark, and look, after this compression there will be spark. So working fluid will expand, so it will force the piston to move down. This is also known as power stroke, because power is generated in a single stroke. Out of four, only one stroke will produce power. And now you will see in the fourth, there is a portion, the operation of exhaust is performed. Look at the fourth position. Look this, yeah, look, in exhaust, inlet, compression, power stroke, and then exhaust. So these are two animations that differentiate 4-stroke engine and 2-stroke engine. So on the left hand side, the animation is of 4-stroke engine, and on the right hand side, the animation is of 2-stroke engine. So in the previous slide where this that was written as inlet manifold, that's in the 4-stroke engine that is attached to the camshaft, and cam openings are here. So there is an inlet intake camshaft, and there is an out exhaust camshaft. So camshaft is responsible for the opening and closing of the inlet and outlet, from where the working fluid is entering and from where the exhaust gases are going out of the piston cylinder. So when the intake camshaft opens, so the fuel vapor mixture enters into the piston cylinder. So here blue arrow, and the piston will move up and compress the fuel mixture. So this is a fuel injector. So for initially air is entering into the piston cylinder, then this volume is reducing and pressure is increasing. So this piston cylinder will compress that air. Then fuel injector will spray a very fine portion of fuel, and this is a spark plug. As you can see that the fire is coming out of that spark plug. So this spark plug will produce a spark, will initiate the process of combustion, and this cylinder will move back due to the power stroke, and at the same time you see that the exhaust camshaft opens up. So as the piston is moving back, then it is moving upward. So the gases that are that have transferred their energy to the camshaft are now exhausted out through the exhaust valve. So this all this process happens in a four different stroke. This is why this engine is known as four-stroke engine. And so in the first stroke, the fuel is entered into the piston cylinder. So in a second, that fuel is compressed in the third stroke, and that is the power stroke. So combustion occur, and piston will move back. And in the fourth stroke, when the piston is moving upward, so it is exhausting the gases out of the piston cylinder. So this process happened in a four different strokes. So if we discuss about the two-stroke engine, so in the later stage we will discuss in detail. So you see that the inlet, so you see that inlet is happening. So two processes are taking place at the same time. So combustion and exhaust, and inlet and compression. So look, as the inlet move here, so inlet, it will be compressed, spark, and it will be taken out. So in a two-stroke, the two-stroke engine perform all four these processes in two strokes. So this is animated diagram of a car engine. So usually you see that I have already told you, or in four-stroke engine, the power is produced only in a one stroke. So one out of four stroke produce power. So we use multiple piston cylinder system. So multiple piston cylinder are used in an engine. So usually if you have happened to have a look in the engine, you will see four piston cylinder or six piston cylinders in a single engine. So why this is required? Because this is required for the smooth running of vehicle. So in automobiles, these four piston cylinder, as you are seeing, are adjusted to some matter that they are in the phase out of. You look that two of these that are in between are opposite to each other, and first and fourth are opposite to each other. So they are in a phase change. So in every stroke, one of the engine is producing a power stroke. So if we talk about single engine, it will be producing one out of four. So when we are talking about four, so in every stroke or in every instant, one of these four is producing a single power stroke, and these pistons are connected to this crankshaft, and this crankshaft is connected to this flywheel. Flywheel is a mechanical device that stores mechanical energy. So you will discuss the designing of this flywheel in the design of machine element subject. So these flywheel are designed specifically designed according to the requirement and standards. So coming back to the piston cylinder and engine. So in engine we usually have more than one piston cylinder arrangement, so that if look if at every instant you see that one of the cylinder is producing power stroke. So as you are moving your automobile, so you do not have deficiency of power on the wheel. So at every instant one of the piston cylinder is producing a power stroke. So these are connected to camshaft. So look here, this is the timing belt. So crankshaft and camshaft are connected with the help of timing belt, and these camshaft, so the opening and closing of each piston cylinder is timely controlled. So these are very delicate. You can see a detailed study of the engine will be performed in the IC engine or internal combustion engine subject. So you will be dealing with the engines in detail in IC engine subject. Now physically you have seen, I have shown you the schematic diagram of the engine and the animation of the engine. Now the definition of some of the important terminologies. So top dead center, TDC, when the piston is at the highest point in the cylinder. So in the top dead center and the bottom dead center. So when the piston is at the lowest point, this is called bottom dead center, and when the piston is at the top point, this is called top dead center. Stroke, the distance that the piston move up and down from top dead center to the bottom dead center is known as stroke, whereas the diameter of cylinder is known as bore. Clearance volume, a volume of the gas in the cylinder when we are at the top dead center. So the labeling is shown in the previous slide as well. You can go back and compare these definition with the actual animation. So displacement volume, volume displaced by the piston as it moves from bottom dead center to top dead center. So as the piston will move from bottom dead center to the top dead center, it will move some of the volume of the working fluid. So that volume that is displaced is known as displacement volume. So these are some very useful and repeated mathematical expression. So the compression ratio is represented with the symbol gamma. So what is the compression ratio? It is the maximum volume divided by minimum volume. So when will be the maximum volume? When the position of the piston is at the bottom dead center. So the maximum volume of working fluid will enter into the piston cylinder when the position of piston is at the bottom dead center. Then it will accommodate the maximum working fluid. And V minimum is the position when of the piston when it is at the top dead center, TDC. So it will comprise the minimum volume, so it will be only equal to the clearance volume. So when the position of piston that is at the top dead center, then it will have minimum volume. So compression ratio is the ratio of maximum volume and minimum volume, and maximum volume will be when the piston position is at the bottom dead center, and minimum volume is when the piston position is at the top dead center. Then we have a relation of mean effective pressure, or MEP. So MEP is equal to W net, or net work done, divided by the difference of maximum volume and minimum volume. So we have already discussed what is meant by maximum volume and what is meant by minimum volume. So if we want to calculate the value of W net, so to calculate the value of mean effective pressure, first you will have to calculate the value of W net. So W net can be calculated with the help of mean effective pressure into area of piston. So area of piston, what will be the area of piston? So it will be, you will calculate the surface area with the help of pi by 4 d square formula. And stroke is the maximum displacement of piston from bottom dead center to the top dead center. So it is also because it is the area into the length, so it is also known as swept volume. So somewhere in your book you might see written swept volume. So because the displaced volume or swept volume, so because that is a cylindrical piston, is in the form of cylinder, so the circular area or cross sectional area, surface area of the piston multiplied by the stroke length is equal to the volume swept or displaced volume. So when it is multiplied by the mean effective pressure, then you will be able to calculate the W net or work net output. So two abbreviation that might come, that are usually used. So wherever SI written, it means spark ignition, and wherever CI is written, it means compression ignition. So petrol engines are spark ignition engine, whereas diesel engine are compression ignition engine. So we have briefly discussed the four-stroke cycle and engine as well. So here in a four-stroke cycle is completed in the four strokes. So in the first stroke, it is the intake. So air fuel mixture is intake. So piston motion is from top dead center to the bottom dead center. Then compression and ignition. So piston will move from bottom dead center to the top dead center. It will compress the working fluid, and then at the end there will be an ignition. And the third is the expansion or power producing stroke or power stroke. So in that the piston again move from top dead center to the bottom dead center. And the last stroke is the exhaust stroke. The piston will again move from bottom dead center to the top dead center, displacing all the exhaust gases and ejecting them out in the atmosphere. So this is a schematic diagram. As you can see, intake, compression, spark, power stroke, and exhaust. So this is an example of two-stroke engine. So second example is two-stroke. So the exhaust and intake happens in a single stroke, whereas compression and ignition happens in a single stroke. So when the piston moves from top dead center to bottom dead center, so it not only injecting or the working fluid is coming inside the piston, it there is also air exhaust. So exhaust and intake are happening at the same time, whereas compression ignition are acting or happening at the same time. So some of the example of two-stroke engine are chainsaw, grass cutter, and motorcycle. So when we are talking about two-stroke engine, so uh, if you happen to look in the Yamaha motorcycle, so people who are using Yamaha motorcycle, it contains two-stroke engine, and you have to add some mobile oil with the oil gas mixtures. So they used to take or inject some mobile oil as well with the petrol. So oil will have to mix. Burnt oil in the exhaust gas usually used for smaller application. So as mobile oil or other oil is mixed with the uh, air gas mixture, therefore it will be burnt with the oil. Oil will be burnt with the exhaust gases as well. This two-stroke engine is usually used for smaller applications. So the comparison between 4 and 2 stroke, that 4 stroke engine has smoother sound as compared to 2 stroke engine. So here you can look and verify that as the piston is moving from top dead center to bottom dead center, it is not only intaking the fuel where but exhaust is also happening. So here exhaust plus intake, whereas when the piston compression and ignition are happening at the same time. So here we will be discussing briefly about the ideal Otto cycle. So ideal Otto cycle was proposed in 1876. So a standard Otto cycle is an ideal cycle that approximates a spark ignition internal combustion engine. The mechanism may go through a cycle but the working fluid does not, because the working fluid after each cycle is replaced and renewed. The Otto cycle is sometimes referred to as a constant volume combustion. So why it is called that? So like other usual process or like Carnot and other process, so it also have four different process. So for process 1 to 2 in isentropic compression, process 2 to 3 a constant volume combustion, process 3 to 4 isentropic expansion, that is a power stroke, and process 4 to 1 is constant volume heat rejection. So because two of the process are constant volume or isochoric process, that is why Otto cycle is also known as constant volume combustion. So this is a PV diagram from process 1 to 2. This is a isentropic compression. From 2 to 3, this is constant volume combustion. So here you see volume is not changing whereas pressure is changing. From 3 to 4 is an isentropic expansion. So this is a power stroke. So in this stroke from process 3 to 4, the power is transferring from the combustion and chemical or thermodynamic energy is transferred to the piston. And from 4 to 1, this is constant volume heat rejection process. So we will briefly discuss the efficiency of ideal Otto cycle. So the heat that is entering or process 2 to 3 is a constant volume combustion process. So this is a according to the first law, Q is equal to W plus U, and so W is equal to 0 because no work is done. So Q in is equal to delta U, and Q in is equal to CV T3 minus T2. And for process 4 to 1, this is a constant volume heat rejection. So similar pattern, Q out is equal to minus CV T1 minus T4. So these we have two equations for Q in and Q out. So the combustion process and heat rejection process, we have the values of heat that is entering or that is leaving. So for the relation of combustion, we have eta is equal to 1 minus Q out over Q in. So as in the previous slide, that was minus V minus C V. So here that minus is multiplied on the left hand side, and the sign of negative is minus minus is equal to plus. So efficiency comes out to be 1 plus T1 into T4 minus over T1 minus 1, and T2 into 3 over T2 minus 1. So this is a simplification. CV will cut off, and here we have taken in the numerator we have taken T1 common, and in the denominator we have taken T2 common. So this is a relation of efficiency of ideal Otto cycle. So efficiency using the cold air standard assumption for process 1 to 2 and 3 to 4 are isentropic, reversible and adiabatic. Thus we use the isentropic relation for V2 is equal to V3 and V4 is equal to V1. Because two of the processes are isentropic whereas two of the processes are isochoric, so the volume will remain constant. So here it is in the previous lecture I have used it as a gamma, so K is the adiabatic index. So here in the previous lecture we have using with the gamma, but in this chapter as gamma is also represented with the compression ratio, so you might not get confused with the compression ratio relation. So we will be using the the symbol of K or kappa against adiabatic index. So T2 over T1 is equal to V1 over V2 power K minus 1. This is a relation we already know for adiabatic. So and for volume and temperature V4 and V3, this is a relation for temperature V4 over V3 power K minus 1 is equal to T3 over T4. So if we want to have a relation between all the temperature, then we have T3 over T2 is equal to T4 over T1, and the efficiency is equal to 1 minus T1 over T2. So here T1 over T2 is opposite, so reciprocal over this. So T1 over T2 is 1 minus V1 over V2. So here the power is A was K minus 1, and here it is 1 minus K because we have reciprocal of it. So RV is the compression ratio. Here we have represented compression ratio with the R and V. So compression ratio is V1 over V2, and we know that the formula for compression ratio is Vmax over V minimum, maximum volume over minimum volume. So at the constant volume process, so the ratio V1 over V2 is equal to V4 over V3. And the efficiency of ideal Otto cycle is equal to 1 minus RV power 1 minus K. So here V1 over V2 is the compression ratio, so we have replaced the volume ratio with the compression ratio. So if we take the compression ratio in the denominator, so it is equal to 1 minus 1 over RV power K minus 1. So this is the efficiency of ideal Otto cycle. So if you don't you might not get confused, so I have written K is equal to Cp over Cv, and that is equal to gamma, that is adiabatic index. So the note is higher compression ratio has higher efficiency. So as the value of compression ratio increase, the efficiency will also increase. But the compression ratio is limited by the combustion knock. So what is combustion knock? It is spontaneous combustion or auto-ignition if any appreciable portion of change resulting in an extremely rapid pressure rise and sharp metallic knock. So if we closely look at the efficiency of ideal Otto cycle, we will come to know that if we increase the compression ratio, so for example the efficiency of certain Otto cycle is 10%, we start increasing its compression ratio, so it is increased up to 30-40%. But after that, if we increase more that in compression ratio, there will be a phenomenon of combustion knock. So a knocking or sharp metallic noise will be coming out of that engine because the compression ratio is limited by the combustion knock. So if we increase that, the health or efficiency will not increase, whereas the integrity of engine will be compromised. So these are the PV and diagram of ideal Otto cycle. So isentropic compression, constant volume heat addition, isentropic expansion, and constant volume heat rejection. So on PV diagram these processes are shown, and TS diagram these processes are shown. In PV diagram, process 1 to 4 and 2 to 3, 4 to 1 process and 2 to 3 process are isochoric process, so these are straight line. And in the TS diagram, process 1 to 2 and 3 to 4 are isentropic process, and these are also straight lines. So deviation of Otto cycle with air standard cycle. So the specific heat of actual gases increase with the increase in temperature. The combustion process replaces the heat transfer process at high temperature, and combustion may be incomplete. And each mechanical cycle of the engine involves an outlet and exhaust process, and because of the pressure drop through the valves, a certain amount of work is required to charge the cylinder with air and exhaust the product of combustion. So these are the reason for the deviation of Otto cycle with the air standard cycle. There is no considerable heat transfer between the gases in the cylinder and the cylinder walls. So these are the reason for the deviation of Otto cycle with the air standard cycle. So students are advised to go through example problem of the topic that we have discussed in this lecture. So you are advised to go through example problem and the problem in the exercise as well. You are required to write an handwritten lecture summary report and send it to my email address arsalan@ciitbar.edu.pk. And students are advised to prepare the lecture thoroughly, because there will be a viva and oral question answer session for every student at the end. Thank you very much. Allah Hafiz.